Yeah.
Hey, hey, Riley and Walter. Great, thank you. And Walter, yes, I know you're pressed for time, so I won't take up too much of you guys' time. So I just wanted to give you a really quick intuition about what kinds of experiments to conduct. And because I looked at the intermediate results and that Riley you sent me, and it seemed to me that there was an obvious follow-up there that you could essentially try out, and which you're going to narrow down and find out anyway. But in the interest of time, if you guys are interested, so I can let you know what the intuition is behind what we're going for, so that you don't really need me after that, except to fine tune the paper and the results and look over the final version of the code to make sure that it's as efficient as possible. I'm happy to do that. But I think that once you have an intuition, which you should confirm today at the end of this meeting, just confirm to me if you guys are on board with it. But you can always reach out to me and say, well, let's have another discussion, another Zoom session where we can talk about this. Happy with that. But the most important thing is to just get a solid intuition about where you're driving with this set of experiments. So it doesn't matter whether it's this field or science, physics, chemistry, does not matter at all, because in every single thing you do, there's going to be lots and lots of little things to do, but there's going to be a goal. So in math, you have this proof, proof this is equal to this, right? But in order to do that, you have to do a lot of these things, and some of them will fail, some of them will succeed, and you got to try this out. Where was I going with that?
Basically a guide for where we're going, you said.
Yeah. So I think that it takes a while. That's where I was going. It takes a while in math, right? Because you guys are done a lot of years of math, so I can feel more comfortable giving you math analogs here rather than computer science, right? So so it takes a lot of while in math to develop a sense of how to prove things. Okay, so because you can work through hundreds and hundreds of proofs, and you're looking at standard techniques used by other people. Yeah, correct me if I'm wrong. Okay, they'll say, well, if in this situation, proof by contradiction. Okay, here you can say, you can take that one-off counterexample and prove it. Oh, yeah, whatever, right? So this standard, tested, well-known methods and logic, yeah, which you just need to know where to apply what. And then you learn these patterns and say, okay, that kind of a block, a stumbling block, in a math proof that you're working through, you're going to say, well, you know what, that pattern I've addressed before using this kind of symbol manipulation to get past it. If you've never done that, well, you don't know, right? So you'll apply that. Okay, so you know that one particular case. Now, another situation, something similar happens, and then you have to say, well, can I match that to some pattern I know? Can I match that to some pattern? So that can only go on for a little while. Okay, so if you are majoring as a mathematician, right, a professional mathematician, it can take you all the way to professional mathematics. So it will take you all the way to a skilled amateur to say, well, I know a lot of patterns. I can, pull these things together, and you give me somewhere, and I can find a way there. Okay, by pulling things together. And sometimes I get stuck. Well, you know what? Even the experts get stuck. So that is the kind of attitude, and it's very similar if you think about it in computer science, right? Because there are things that people can put together without having so it's CS2B, having done 2B and 2C, you have a lot of intuition about computer science. That's why I don't want to go into that territory. But but you can now relate to what I'm saying, because there's a lot of people out there who you don't have an intuition about what they're driving towards in computer science. And they're just trying, well, let me try this and see if this test passes. Try this and see if this customer is happy. But they don't know. They don't know what they're driving towards. They're just trying different things. Yes? Okay, so, but the thing is, everybody starts out like that. Everybody, every single person, every single learner, every single child starts out like that, in my opinion, is trying different things, seeing what works. Now, the people who become professionals are the ones who say, I'm not happy with just what works, right? So, because I know, because, I got a lot of things that work, and I can use them to be happy, but I'm not happy yet. Because what happens if those things are not available to me? What happens if these standard patterns didn't exist? How can I improve this? Yes. So a professional will say, well, I've got enough to make a lot of money now. Well, not a professional, right? It's a skilled amateur. Even in computer science today in the Silicon Valley, you'll see a lot of people, right? They don't have a solid intuition about computer science. They know a lot of these little things that they can bring together to bear on a problem and probably solve it in an inefficient way and get money. And they get lots of money too, right? So they're well off and, driving Ferraris, I don't know, who knows, right? So this is, and then they think that's what it is. That's what computer science is. But they don't have an intuition. And so they're not professionals. They're just skilled amateurs. So the ones who go past the Ferraris and say, well, you know what, I can get all the cars I want, I can get laid as much as I want, I can get all the mansions I can buy, right? These yachts and all these things. But is that enough for me? Right? Because what happens if in a hypothetical quantum world, okay, some other world, because it's equally likely, right? You step back and say, you know what? Oh my gosh, I'm so lucky here today. But I could have been totally unlucky because there's like 4,615 incidents in the causal chain leading up to my success today. Right? It's not 4,617, but you get the idea, right? There are lots of things I control and I led towards my success. Yeah, totally fine. But there are lots of things that could have gone wrong with equal or higher likelihood, but they just lucked out. Now, 99% of the time, because of ingratitude and arrogance, I think those are the two causes that I can point at, we don't even see, right? We're not grateful and we're arrogant to think that we're so good that everything will just work for us. So things that naturally automatically work for us, we just overlook. It's like the air we breathe, but we don't see it, right? It keeps us alive, but there's absolutely no recognition of it. And so these things will just go, right? They come into your life and they'll go. There is no chance of that and that experience enriching your life because you were not humble enough to learn from it. And only humility basically teaches us lessons. That's why, we end in the mouse and say, you start off as a roaring tiger, but we end as a humble mouse, saying that, well, now I'm ready to learn. Until now, I wasn't ready to learn. At this point, I know enough to be able to ready to learn, because not everybody can learn. Only people who really know can start learning. Everybody else, until then, is just getting prepared to learn, right? And you get a lot of money just to get prepared to learn. So that is my opinion anyway, and it could be totally wrong according to your experience, so you can check it out. But how does that so the professionals who say, I'm not happy with power, glory, and fortune and fame, okay? I need to get to the root of the matter, because in some quantum world, some one of these extremely likely situations, all of those goodies that I got that were responsible for my success could not have existed. So does that mean that I'm screwed in all those worlds? Right? Because I enjoy the success I have, but it's equally likely that I could have failed miserably and everybody would be laughing at me. So if that was a situation, do I have it in me? Right? So then they say, well, okay, I'm secure and rich and happy, but I want to make sure that I will be secure and rich and happy, even if I didn't have all the lucky things that I had. Does that make sense? So that is going one step above what, common civilization teaches us. And saying, well, you know what, we get everything. At some point, science is going to give us everything. So the question is, are we going to be just happy? Saying, I'm happy with what I have, or, or I'm going to keep on shooting for Mars, or, keep on going for higher and higher goals without knowing what you're going for, right? And so when you say that I'm going to get to the bottom of that, those are the people I find that will actually eventually get to the intuition and saying, okay, now, a million intelligent people around me have told me these patterns exist, but how did they come up with these patterns? So I want to have the exact same ability as them, so I don't need any of these patterns anymore, because my brain is too valuable to store static information. Yes, because anything that can be computationally generated, like the towers of Hanoi, where you only store the most recent level, okay, and everything else is computationally regenerated, because otherwise you'll be filling up the cache every level, right? But you're saying, well, you know what, it's a 2DN, and so I want to not store everything. I just want to store just enough bits. And so you would say, well, you know what, I don't want to memorize these individual data points. I want to learn the equation of the curve so that I can just get by with 5 floating point numbers, and I can generate an infinite number of numbers from there. So I fit the line. And so only the totally determined people who are not happy with making a living, making a comfortable living with a profession will go on to that stage to say, what do I need beyond a comfortable living to actually feel totally at ease, so that if this comfortable living was absent, I can just regenerate it, or I don't need it. So that intuition is what we go for in all problems in math. You would probably, right? So that you could relate to that. Well, anyway, so as far as play goes, this is the intuition, and you can try and drill down into it. And if you have any questions at any point, you should just feel free to ask me, and I'm happy to have another session and explain the technical details of it. Okay, so the experiment that Riley most recently ran, and correct me, Riley, if you're wrong, is to take a single target value and get it like 5,000 times from splay trees, right? And then take the same value and get it from 5,000 times from an AVL tree. Now, because the average access time is log n for AVL trees, we're talking about 5,000 log n for AVL. Whereas here in a splay tree, in the worst case, it could actually be n, O of n, yes? However, it is O of n only once, because once it is accessed the first time, it's going to sit at the root. So what you have on this side is essentially n, which is the number of 5,000, which is the number of accesses, plus n, which is the speed of one axis, the first axis, the worst possible axis, divided by 5,000. Yeah. So that basically simplifies to 1 plus n over 5,000. Yes. So you know that is the overhead of the splay tree, and you know that as soon as the denominator, that 5,000, keeps increasing, the number of times you access it, the average access time of the splay tree is going to go down. Now that is for the extreme case, right? So the reason I wanted to paint the extreme case is that now you can, the two extremes, and then you can actually find the experiment that gives you the best possible distribution. Okay, so I say that's the extreme case because we said we're going to look at not a modal distribution. Well, technically it's a modal distribution, but it's a limit of the modal distribution because we're going to look at an impulse, which is basically you have all possible numbers, but we're saying only this number is likely, one line. Yeah, because we're saying my target is exactly one number. So you have an impulse there and everything else is flat. Now that is the extreme best performance you can get from a splay tree, which is only determined by the denominator, which is the number of times a splay tree is accessed for that target value. So far are we on the same page? Just if you're out of step, let me know so I can just make sure that we're all on the same page before I keep going on.
Yeah, it's okay.
Yeah. Okay.
Yeah,
great. And it's all recorded too. Yeah.
I have one question about that. So what confuses me about that is when I look at the data that we got from the one Riley sent in the email, I'm surprised to see that the difference in the AVL find and the splay find was not that big for repeated lookups. I thought it would be bigger for that, since splay should have it at the root and it should be extremely efficient at that. So
are you talking about a uniform? Are you talking about a uniform distribution, or are you talking about a modal distribution?
Oh, that was for the modal distribution.
It was for the modal distribution?
I believe so, right, Riley?
I don't remember which way I ran it. I can run it again though. It wouldn't be an issue.
Regardless, we'll just take the search or find experiment that Riley is running, right? So we just start, yeah, and in fact, we can forget about the modal distribution, because the modal distribution is we're talking about the extreme modal distribution, which is just one target value. Everything else is zero probability, and that target value is one, right? That is the best possible case for a splay, isn't it? There's only one possible, so that's always at the root, and it's O of one axis. So we know, and so that the reason I describe that case is because it is easy to test and verify. Because you can verify that if I keep getting the same target value, the performance of the splay tree you can provably say that it's going to get better and better only. There is no way it can get worse, because the found element is going to be at the root, and that's the only thing that's going to be accessed, right? So the more times you access it, the better the splay performance becomes. This denominator keeps increasing. Yes. So you have a guaranteed case where you can actually check in your debugger that, okay, we know for sure that the splay is better than AVL, for, I don't know, some n accesses of the same target value. That has to be provable, and that is actually borne out by Riley's data. Yes or no? The same target value.
For splay, yeah, it's a higher value immediately, and then it drops off because it gets constant
Yes,
access.
yes,
Mhm.
yes.
Yes.
And
And it's
that is,
also,
and
it's al-
one sec, Walter, when you said higher value, I missed, I don't remember the exact details of the data. Is it higher than AVL and then drops, or is it, as bad as AVL and then drops, or as good as it?
Is, let's see.
I'm looking at it now, and it looks to be it looks to be a bit higher. So AVL first one was 0.01, and this one's 0.011. So it's a tiny bit higher than the AVL.
Yeah, that was a weird one. I didn't understand that either. So the
No, it
splay-
has to be worse. The first access has got to be worse than an AVL, for sure.
Yeah,
is
I
that-
understand that part. Yeah. Mhm, I
But is that
understand
not what
It's
you're
just
saying?
For the
Yeah,
no, for
that-
the AVL find of that number, the AVL one starts very low, goes high, and then goes back low. That was the only data that I didn't really understand.
Yeah,
Okay.
the first is faster than the second one.
All right. Okay. Can you tell me if you took a target value and accessed the same target value from the AVL tree, let's say 1,000 times?
I didn't do that many samples. I just did a handful, but I can run more samples for sure.
Right. Just, well, it doesn't matter. So 1,000, or maybe let's say you ran 100 times. You take one value, pick a value at random, and you're going to look up the AVL tree 100 times.
Mhm.
And you've already made the AVL tree, and the AVL tree should have, I don't know, 20,000, 100,000 nodes.
Yeah, they're
Make it have
both trees are identical. Yeah.
Yeah. A million node AVL tree, and whatever that big size is, okay? That huge AVL tree, and you're going to pick a random value, and you're going to look up that value from the same AVL tree, I don't know, 1,000 times, right? Let's make it 1,000 times. Now, that is, and then take the total time taken, and you have to be careful to only calculate the time over the find, right? Which means you have to make the clock call before the find call, and
Mhm.
make the second clock call immediately after the find call, right? Because you can have lots of other code. I haven't looked at the details. That's probably how you're doing it. So the total number you have is the time taken by 1,000 finds. Yes. Now that you divide by 1,000, and that is the time taken per find. Now, okay, all right, that is not the number, because is that the number we're looking at right now? Well, assuming you got a different number of.
I just took it was a small test. I just took direct times. I didn't divide. I didn't do 1,000 runs and divide it by 1,000 or anything. Just printed out the direct time.
Direct time meaning system clock. You just
Yeah.
before the program started and after the program started,
Mhm.
ended. Oh, totally no. All right, never do that. Okay, so because the overhead is too much. There's too much noise that way. Right?
It was
So-
just right before the find. So I
Yeah.
grab the clock value, find, and then take the clock value minus that previous clock value to get the
Yes.
time taken.
Is that how you're doing it now?
That's how I did it for these tests. Yeah.
Oh, that's how you did it for the tests.
For the
And-
ones you're looking at in the it's the test times document that I sent.
Oh, I see. Okay, so you are doing it the right way then, right? So the clock reading happens immediately before the find and immediately after the find. So basically, it just envelopes the
Mhm.
call.
Yeah.
Okay, and then you divide by 1,000 or whatever that number is, the number of
I
times
didn't
you
do that
input
for this test. I just took direct times per each call.
it. Okay.
I had
For
this in
each-
a for loop. So for this one, I only
Oh,
ran-
yeah. All right. So no. So all right. So you're going to take one value, find it 1,000 times on the same tree, exact same tree, and
Mhm.
divide the total by 1,000, and that is the time taken per find.
Mhm.
Now, that is not the number where that is still not the time taken per find, okay? Because that is just one data point. So we've done that to get one data point. Because your AVL tree is fixed, right? You could have lucked out with whatever that log n search is, that the target you're finding could be close to the root. Yes.
Mhm.
So you could have totally lucked out there. So what you have to do is that now you got this structure, you got to put that in a second outer loop, okay, which regenerates the AVL tree from scratch using a different random seed. Another million nodes. So this time you use random seed 2, random seed 3, and you got to do that 10 times. And take the average of those 10 averages, and that is your find time. Does that make sense?
Mhm.
If not, just let me know. Okay, I can just break it down into individual bullets in an email and send it to you. But I think you get the idea. Now, with Splay, you do exactly the same thing. And then the numbers will start making sense. And then we can also start looking at the efficiency of the individual code and see what we can, needle out and make sure it's really efficient and all. So then we'll have these numbers side by side. And basically in your data, just simplify the spreadsheet too, right? You basically say one table for uniform distribution, another completely different table for, I don't know, what is it? Modal distribution. Okay, on the table with the uniform distribution, you say time taken per find, time taken per, I don't know, insert, time taken per, right? And then you can have a star on the table, and that says, and the star, the asterisk, you can say these times are actually averages of, I don't know, 10 runs, each of which used a separate tree of 1 million completely random numbers, different from the previous run. And using that tree, we did 1,000 find calls and averaged over them. So each one of those numbers, you don't have to, right? That's all. You only have one column of numbers here, one column of numbers here. Then we can compare them side by side. There's no, we don't need to do some, mental juggling there. I think it'll be easier. So, but the intuition I think you probably have now is essentially saying we have one extreme end where we can be guaranteed that Splay is better than AVL, right? Because Riley's experiment shows it. Riley's experiment shows that if you have an impulse, a Splay is definitely better than AVL for 5,000 calls of the same target. Yeah, because the same target is what it means. The same target, calling a same target means it's an impulse. It's a modal distribution. Now you can say, okay, now let's say it's not an impulse. Maybe it's actually a normal, but it's a very pitched normal, meaning that you have one target, but you also have two numbers on either side. So there's only 3 numbers you can call. Yeah. And pick 2 numbers on either side of it and try the same experiment. Right. And with that, you can actually try and invoke your find on, let's say you hand construct numbers that you're going to pick from the distribution, right? And say, these are the numbers I'm going to keep call, this many times I'm going to call this number, find this number and so on, right? So you can, so the middle number is going to get called 80% of the time. Yeah, and pick the standard deviations, right? And these 2 numbers are going to get called, I don't know, that many times. And at some point, when the modality of the distribution settles and it becomes decurved, it'll approach the uniform distribution. And at that point, you will actually be able to narrow down and say, at this point of flattening of the distribution, the Splay tree becomes as performant or worse than an AVL tree. Yeah. Now that is a very insightful comment in your paper, and it will actually get cited, I think, because it actually gives objective grounds for people to use. And I'm pretty sure someone will pick it up and say, well, you know what, we can actually do a mathematical derivation of the point in a distribution where you can make a runtime distinction between whether I use a Splay or an AVL. Yeah. And it's always fast. So these kinds of sophisticated data structures might come out. But people are already doing these kinds of things. But I think the important thing is to just put these numbers out there, saying in terms that anyone, especially future students of C2C, can understand. Saying, well, you know what, this is what, and the reason we're doing all these averages is to basically drown out the noise. Because what if we lucked out with an AVL tree? These numbers totally don't make sense, right? We can make conclusions out of one AVL tree. So our conclusions should be based on 1,000 different, eventually maybe 100,000 AVL trees. I don't know when you run it overnight now, right? So, but right now, see how much you can get by running timing your experiment to run for 2 minutes or 10 minutes, right? So you say, well, if I have 10 minutes to run my experiment, then I can do 1,000 different million node AVL trees, 1,000 different million node Splay trees, same, right? Same million numbers. And then each one of those, I can issue 1,000 find calls, 1,000 find calls. Yeah. So that's what I can do in 10 minutes. And then I can come back and those numbers will be totally solid. Now, that's all it is, right? So I was very sure that you are very close. You guys, you're narrowing in, and the kinds of issues you're running into, and the problems you're, running into, and the numbers you're generating. It seems to me like you're very, very close. And so I just wanted to fill in this little bit of information to say, here is your end post. Here's your goal post. Your goal post is, now you've proved it empirically because you have it right in front of you. Riley's experiment says, for an impulse, which is the ultimate modal distribution, right? I can prove it empirically that the splay tree is better for, 10 indications of the same, right? So you have one goal. The problem always arises if you don't know where the end is, then you can't calibrate. Yeah, so now you know the two ends of the spectrum. One side is AVL, which is log n, and the other side has got to be splay with, the modal distribution, which, approaches O of 1. With increasing n, a splay axis, a splay tree performance is actually O of 1. Think about it, right? So O of 1 in the limit, not, in the limit, O of 1, not in the limit of number of axes, but it is in the limit of the, distribution. If the distribution gets more and more peaked, the performance of the splay gets closer and closer to O of 1, right? From log n to O of 1. And it'll be very interesting to find out exactly the point at which it becomes worse than log n. Because it starts off at O of n, and as the distribution gets more and more peaked, it's going to be O of 1. So it's got to cross O of log n somewhere, right? So what is the point at which it crosses O of log n? And that's a very interesting theoretical question, isn't it? This is a Don Knuth type question, right? So you can actually post this on Stack Overflow. I'm pretty sure that there are people, who've maybe one of Knuth's students or someone, who've thought about these and say, okay, you know what? I also had the same thought, and this is what I derived, right? And they would share that information, and lots of people will find it interesting, I think. Right, because it's all part of fundamental data structures, right? So you're developing such a sound grounding on these data structures by doing these extended experiments. And that's what I think is more valuable than learning these individual data structures, because you can do CS2A, 2B, 2C, or equivalent course in any college or university. Now I know how to use all these data structures, but the real value, I think, comes from not just knowing how to use them, but knowing how they do these things and saying, even though both splay and AVL do the same thing, in this situation, this is better. But how many people say that? In all of the people I've employed, only 1 or 2 people would actually know enough of the data structure to actually make that call. But most of them are competent and good enough to say, okay, well, if you want to use a splay tree, I'll do it, right? Because they know how these things work. And so, a director or a manager could basically say, well, this is the bigger project, and this is how we're going to do this, and we need a splay section here, and so on and so forth. You go and do this, right? They'll go and do it because they know how these things work. It's just, it's like going from the basic dancer to an expert dancer, where the basic dancer can do all these individual dances very well, but the expert dancer can also stitch these dances together to build a bigger performance, so that seamlessly move from one thing to another. That's why you go to these ballets and all these performances. You see 2-hour programs, and you think, how the hell could they even remember how to do these things? But they have done these individual bits, and they just splice them together. And it's not just random. It's not just even practicing splicing together, because I've been to performances where it's completely extempore. It was an audience request, and someone said, we'd like to see a dance of this particular song, and it's like a 10-minute piece. It's not like like a 2-minute piece. 10-minute piece. And she just had to think about it for I don't know, 10 or 15 minutes. So yeah, let's do this. And they're all complex moves. Here is a complex move. There's one. It's not complex all the way through, because the piece has fast sections and slow sections, and fast sections and slow sections. So you got to stitch these things together. And for beginners, yeah, okay, even though I can do the fast ones fast really well, slow ones slow really well, but transitioning from one to another or fast to another fast, those are things that takes a little bit of time for beginners. So once you get really good at doing the individual dances, the next thing to focus on is to say, well, how can I transition from one to another without anyone noticing? Right? And not noticing in the bad way, but noticing in the sense anyone who notices things is basically jarred by it. You don't want to jar anyone. So you just want to say, you want to coast along, like a bird in the sky, they say, that leaves no footprints, right? So I just want to make sure that you don't do anything alarming. and these are things that will set you up. Even in human relations, I find that people who can think fast are not alarming to deal with, because they don't make off the cuff decisions all of a sudden that totally surprise you. Because I think about it, and chances are that if you're in a discussion with a really intelligent person, they've actually been in your shoes, or even because they're a fast thinker, they can actually simulate what it's going to be like in your shoes before they open their mouth. Right? So when you say something, before they respond, they have 10 responses in their head, and like Grand Chess Master, really, right? Because they will be able to play it out. If I say this, if I make my personal response as this, that's what that person is going to say, that's what this person is going to say. So let me create this quantum world out there, okay, where I'm going to be inhabiting all of these people, and I'll find out what their expected responses are going to be. So they are able to, we think as humans, this is all very difficult to do, right? You need a supercomputer to do these things, but people have been able to do this, right? Just with extreme concentration, patience, and practice, you can actually empathize very strongly, because empathy is, I think, right, just the ability, high-powered computational ability in your mind to be able to simulate what goes on in someone else's head accurately, right? In order to simulate someone's thinking accurately, you first have to decouple it from all human values, right? Social values, because social values may be different for that person, right? And if social values are driving your decision, you're never ever going to be able to simulate from something in their head. So that is the most important skill in being able to develop empathy. But 90% of the people out there I see, they haven't mastered that skill. So they always react to other people's behaviors based on their own cultural and social norms. Whereas we have no idea if that's what the other person is thinking. So it could be perceived completely incorrectly, and misunderstandings arise, even between countries and nations, and all kinds of crazy shit happens. And I think that, practicing thinking systematically, and that is how I think also practicing should go. Computer science, or even thinking, right? People, and this from experience, right? In programming, 2A, 2B, 2C, tell me if I'm wrong, okay? When you have a problem, if you sit down and think about the problem in a focused way and try only solutions that you have already thought about in your head, okay, you have a much better chance of solving that mini and moving on than if you were to try a million different things endlessly. All right, which I've seen from so many programmers now. I have a flurry of 5,000 submissions from the same student, and that doesn't, they haven't made any progress at all. And the reason for that is because they have also spent the same amount of energy as you, except that they're spending the energy physically, right? Whereas you're spending the same amount of energy mentally. It's a whole lot easier to move electrons than to move these atoms in your hand. So anything that is mediated by mechanical processes is hugely limited compared to what you can do in a computational or mental process. So by learning to decouple and say, I'm going to run the simulation in my head, then you'd be able to go through, zip through. And it's going to be difficult initially, right? But you can zip through all of these simulations and say, and those are the people I also find, more compassionate in general, because they can feel for you. They know what it's like to be in your shoes. And I don't know, we shouldn't be talking about that shit. But essentially, computer science is essentially just slowing down and saying, I'm going to, practice not firing in all directions, because I'm still, same brilliant person. I have the same amount of intelligence as someone who's succeeding. I'm not succeeding, and that person is succeeding. And I can't believe that we're unequal individuals, right? We're both equally gifted, right? But that person succeeded and I failed. And it's probably because their energy is focused in one direction. My energy, the same amount of energy, is focused in multiple directions, and some of them are canceling each other out. So let me first, sit back. All right, I'm not going to do anything at all, because anything I do is canceling things out. So let me just sit back, right, and first figure out what I can do, right? So, and then they say, and thinking about it, they'll say, okay, well, I've got my focus now. Let me just try this one thing. Okay, I don't want to do many things, because then many things I can, I'm back in the same boat. I'll try one thing at a time. When I've got really good at one thing, then I'll try one more thing. So, and that's why in college, I think, right, this is my opinion, and college, I think a lot of students make the huge mistake, okay, when they enter college, saying, I'm going to do so many things. I'm going to participate in this club. I'm going to be president here. I'm going to be leading this thing here. I'm going to start a new thing. And I'm going to do research in 5 different areas and impress 7 professors. Okay, that's the stupidest thing to do, right? It's not as though you're going to die tomorrow, right? So, so we say, you know what, I'm going to do one thing first, really, really well. And I don't care about other things. All the other things I just need to do enough for sustenance, right? But I'll get really good at one thing, which is my interest. And when I'm really good at that thing will keep me alive for the rest of my life. Now I can focus on all these other things. You can add, but if you add one at a time, you can add any number. But if you try to add many at a time, you'll add nothing at all. That is my experience. I don't know if it's worth anything to you, but try it out. And if it works, I think it'll be great. So as far as play goes, I think this is what my thinking is. So you've got the endpoint. Make sure that you don't lose that endpoint, because if you find at any point in your experimentation that play is not behaving properly, by which I mean it is actually worse than an AVL tree when it should be better. Meaning that at some point, it is actually it should be better than log n, because I've only got the impulse and 2 numbers on either side. It should be better than log n, but it's not better than log n. So you have enough information now to debug it. Yeah.
Yeah. On the topic of the performance of the trees, the splay is much faster, excluding the find for now, which we're still working out some things with that. But it's much faster than the AVL by a significant margin. I was wondering if that's what you expected, or if that would hint that maybe there's an inefficiency in our AVL implementation.
I don't know about the significant margin, because I don't know, because this is the first time I'm actually looking at results from such an experiment, and it's probably too early to make the call. What all we are expecting right now is that this is our intuition and theory, which you guys will probably find out if it's true or not, and which we know already is true, because we know for an impulse display is better. Riley, you ran the test, yes? So we know for an impulse display is better, and keep the denominator at 1,000. Okay, run it on 1,000 different AVL trees. 1,000 different splay trees. The only relation between the two is that splay 1 is made of the same 1 million numbers as AVL 1. Splay 2 is made of the same 1 million numbers as AVL 2, right? So you got 1,000 on each side. And on each of those trees, run 1,000 finds of the same number. So you actually got 1,000 times 1,000 things to do of million items in each of the trees. So it may be an experiment that takes 10 or 15 minutes. Or even a whole hour, but I think it'll be worth it. But at some point, if the numbers don't start making sense at all, I will absolutely dive in. And by the way, if you want to use my reference code, I think I've spent a lot of time, making it fast. So you can just use it. Don't worry. Okay, so just use that code. You don't have to attribute it in, because you've got it very similar anyway. So just
I've ingrained it in already to mine. I didn't want to copy too much word for word, but I got it in like 10 microseconds. So
it's yours. Okay, so don't worry about it. So take we'll do an AVL implementation also. We'll do an efficient AVL at some point, but we want to make sure that the trend holds up. The trend in our mind, which is this is what we want to see, right? And I think a lot of people want to see that too, because the theory says AVL and splay, and this is where you use that, and so on and so forth. But many people don't even know. Even in our lecture notes, I don't think it makes the case that for a modal distribution, a splay is better than an AVL, and this is the place. This is the variance. Because if the variance is low, you approach an impulse, right? If the variance is high, it flattens out. So at some value of the variance, a splay is going to be better than AVL. Yes. So it'll be interesting to find out what the variance is. Because we know for sure that if the variance is 0, which is the impulse, and impulse is basically a Gaussian with variance 0. Yes. So variance 0, we know for sure that AS plays better, and some big ass variance like uniform, we know an AVL is better. So at some point when the variance, because the variance is a continuous variable, isn't it? It goes from 0, yeah. So at some point in the variance, the display becomes better. What is that point? Okay, I think that's an interesting mystery, isn't it? Okay, so you can actually make that a mystery paper, saying at some point display becomes better. What is that point? Okay, and that would be really cool. No, was this useful? Because all you need is just to figure out what experiments to run next. So you don't need me at all. So
Mhm.
you just need me to unblock you if there's something that I can't do, which is fine. You can ask me, right? Maybe there's something you've forgotten and I'm happy to help out. But generally, I don't want you to be stuck where, you don't need my permission or input on anything. Just keep going ahead. Your goal is to produce something that's interesting and worthy of people reading. And once you have the intuition, I think you should be able to do this. Was this useful? Do you know what you're shooting for, right? You have these two extremes now bolted down because you can both sides you can experimentally verify. All you need to find out is where it starts getting better or worse. Yeah.
Yeah.
By variance. Yeah.
Yeah, this was great.
At some point, do some research into there's a random class in C++. Okay, I think it's a random number generator class, but it's not rand. It's a random number generator, and that generator, I think it's called randgen. You can configure to spit out a particular distribution.
Oh yeah, I've been looking at that on Stack Overflow. I don't know if it's the same one, but
It must be. If it's on Stack Overflow and C++. Right now, the cool thing is that I think you should be able to parameterize that class with I want a Gaussian with a variance of 0, and you should get an impulse function from it. Or you could say I want a variance of not 0 but 0.1, 0.2, 0.3, 0.4, and so on and so forth. You can change the variance, and you can say and you can use that number to generate your randoms. So you're not doing these funny things like adding up your uniform rands to generate your pseudo Gaussians. You're actually using the random function to generate an actual Gaussian with a controlled variance and mean. Then you have everything at your fingertips, right? You can say, right, if I set the variance to this display is better. If I set the variance to this, AVL is better. So if you do that, I think it'll be really cool. But before that, just make sure that with the approximate Gaussians that we're generating with adding these numbers together, yeah, our intuition is still is holding, meaning that we've nailed the two ends down, and we want to get closer and closer. At some point, when the distribution flattens out from an impulse, at some point AVL gets better. What point is that? And in fact, you should be able to plot a curve, right? You should be able to plot a curve of AVL performance and splay performance, right? With variance on the x-axis and AVL performance and splay performance. And you'll see that as the variance goes from 0, where a variance 0, splay performance is here, and AVL performance is log n. Yeah? But you'll see that, variance, maybe take 15 different variance samples, or, 100 different variance samples, 0 to 1, 0 to, let's say, 10 or something like that. I don't know, some number, 10% of the whole, right? Right. So you say, right, so I have these different variances, and as the variance gets bigger and bigger, the performance of the display is going down, but this one is constantly log n. Yeah. But at some variance, the display performance dips below the log n line. So you can actually, that's a very interesting graph to say, here's a display tree performance, here's the AVL performance, and here's the variance of the distribution. Those are the only three things that will matter. Yes.
So that point of intersection then will be the exact point of where AVL and display are equal. Yes.
Yeah. This is really cool, isn't it?
Yeah, that's very interesting.
Yeah, and I think it will be a very worthwhile paper. It is, I think it will be very nice to read, and lots of people will be interested essentially to see. Wow, I always suspected that to be the case, but here are two students actually went and improved it, right? So that'll be really cool. I don't know. This was useful. Yeah, was this useful?
Mm-hmm. Yeah.
Great. Just feel free to call me, okay? Just like this, so let me know if you guys want a Zoom session, and we'll just organize another chat. Email is fine too. Just keep, sending me email. At some point, I will definitely look at all the Git code and make sure that everything is buttoned up, and AVL is also, made as lean as possible. Yeah, made as lean as possible. If it's not already lean, which I suspect it probably is. But there's always scope for one extra eyes, one extra pair of eyes, or say, hey, you know what, there's an extra addition in this loop we can get rid of or something. All right.
Okay, awesome.
Thank you all. And Walter, thanks for taking time off your schedule. How many courses did you say you're doing? Math course, and then
I'm
more.
I'm just taking the math course right now. It's I'm having a bit of trouble with it just because of the type of content that's in the course. So it's a lot of time on it, but I will be done at the start of August. So if we do want to do more about that, we'll look at the AVL display.
Yeah, totally. We can keep, you guys can keep this as an open project, meaning you get one report out and then you're doing more, extending that. Obviously you already know that, you can do the same thing with the hash table, because a linked list hash table where you actually have, there's so many sorting, so many things you can do, and you can do all these experiments into your Harvard's content. Yeah, don't worry about it. Yeah, I know math could be just like computer science. It's like doing two difficult computer science courses at the same time. Is it 1D or something, vector calculus?
No, it's 1C right now, but it's over the summer, so they kind of push it into much less
What is
time.
it? Different differential equations?
Yeah, differential, and you start to get introduced to linear stuff as well.
Is it Zach's class? Are you taking Zach's class?
No, I'm taking Professor Nosratia, I think her name's Dita Nosratia.
Oh, not at Foothill.
Yeah.
Oh, I thought I knew everyone in there. Yeah, because Zach and I used to work on the curriculum committee together, and then he was teaching Math 1B, and he used to come to our meetings, and before the meeting started, he showed me all these really cool animations he developed in Mathematica, for these surfaces and gradients and all. And I know lots of professors just teach them, hand wavy, or with equations. But he used to make these videos, wireframe diagrams in Mathematica, and just watching them was really cool because it's 3D and it's all animated and surface moving around and different colors. It was really cool. So I was very impressed by those things because he put the effort into time to generate those things.
It's
yeah,
really
maybe do
fun.
Yeah,
it's really fun because I remember doing in high school. I did a little bit of work with Unity and making some games for a class we had, and I remember not understanding how to do some of the math for 3D spaces, and now I'm learning that in math class. It's cool to see that connection.
Fantastic. That's very cool. But after you guys finish this, you want to do a project with Oculus and what is that? What is the C++ thing? Unreal. It's just like Unity, except I think it's more powerful because it just goes. So I can. In fact, my 2B students, they're actually, they're really jazzed up. I think I told you this, right? Because this batch was really good and people were following what you were doing. And I got a lot of really good 2B students now. And some of them are at UCSB and UCLA. And I was thinking of, over summer, most of the students don't have anything to do. They'll end up playing Fortnite and wasting it away. So I said, I'm thinking of saying, you guys can run a Questathon at your universities. And I'll be happy to sponsor an Oculus Quest 2 for the first prize. Meaning that all the contestants will start with, red 1, and the first one to reach red 9 and ace all of them, not pop. Ace all, complete Quest 9 and also get the maximum number of trophies. Yeah, I think that's how I'll do it. Okay, that's what I'm going to suggest to them to say, because they'll run the contest. Say you have to complete Quest 9, but the winner is the one with the max number. To qualify for the prize, you got to complete Quest 9, but the winner is the one with the max trophies after completing Quest 9. And I can buy 2 Oculus Quests, I guess, 1 for each college. I don't know, something like that. But it'll be fun because these things you can C++ also you can develop on. So really cool. I can totally help you with these things. And if you guys want to run Questathons, among your classmates or friends or relatives, and say, get 10 people, because 6 weeks of summer, what are they going to do? Most people, right? You say 6 weeks. 6 weeks, you're going to solve 9 quests, and the first person to the end with the max trophies will get a Quest 2. Okay, you solve the question, you get a Quest 2 Oculus Quest 2. Maybe something like that. Yeah, so if you want to do that, I'm happy to sponsor it or something.
Are you teaching 2A in the fall?
Yeah. In fact, I kind of decided to retire in a couple of years at the end of 2025. So I only have like 2 more academic years. I can, I'm planning to teach at Foothill. So I want to offer all 3 every single quarter so that all the students, they maximize the chances of people who want to do it with a question system. Because I don't know if they'll continue to offer questing after I'm retired.
Yeah, my brother's starting, so I'm going to try to get him to enroll in 2A.
Oh, cool, great. Yeah, and don't yeah, obviously, not to help him with the actual code,
Yeah.
but having someone at home who's done, C++, I think is a great help generally. Not to ask you for solutions, but just so you'll know, right? So you'll know, well, that person has also done this and they're still alive. They're drinking coffee right there. So I can try this too, right? So I think it's great. All right. So and so keep working on these things. It's fun, and also think about getting other people to question and ask your brother to start questioning already. He save a lot of time once he enters to it.
All right then,
All right.
guys. I will see you next time if we have another meeting.
Sure, and let me know how it goes, and I'm looking forward to all the numbers.
Yeah, I'll keep you updated through email as usual. All right. Bye, guys.
Goodbye. Best of luck, Walter, with your exams.
Thanks so much. Goodbye.
Bye.